Okay. Perhaps we should start if anybody turns up. I'm sure they wouldn't have missed much. Okay. New faces and familiar faces. So I'm Chris Pryor. I run what we fondly call Aztec South down at the Rutherford lab, where we specialise in protons more than electron machines, which is the tendency up here at Daresbury. And I'm also, well, now Emeritus Fellow. I retired last year. For getting on for 40 years, I was the senior mathematics tutor at Trinity, Oxford. So the fact that I was a mathematics tutor tells you the sort of orientation that comes into this. So, and I should have given the lectures last week, but I was meant to be in China. In fact, I was supposed to be in China for the whole of October. And I tried to pass on the lectures, and Jonathan Gratus said he'd do the relativity, but he declined to do the electromagnetism, which is a pity because the two are tied together. And in the end, the China trip fell through anyway, so I got the electromagnetism back. No one else?
Not from any offices.
Yeah, that's okay.
Stuck on transport.
That's okay. So, I don't know, I assume Jonathan just used my slides. And since he doesn't have a Mac and he doesn't have the same operating system, he couldn't actually use them as they were. So I had to give him a PDF, and I gather there was 150 odd slides or something like that altogether. So if you've got a great printout, I'm sorry, you weren't meant to have had that. It's normally only about 40. But with all the overlays and things, of course, each slide turns into 4 or 5. Anyway, so this week I'll try and give you the right printouts. And as Jonathan should have said, these are just meant to be revision reminders. If you're starting off on a PhD, they're just meant to remind you of things that you probably did in your degree course and that you'll need depending on which area of the accelerator world you go into. So basically, electromagnetism, it's just Maxwell's equations. It's just to review Maxwell's equations and what follows from them. So I guess quite a lot of it is just reminding you what these equations are. I put a little bit in. Again, it's just a reminder. It should be really familiar. What happens to a charged particle if you put it in constant electromagnetic fields? I'm going to mention, because as I said, these lectures are tied in with the previous two on relativity, how electromagnetic fields transform under relativistic transformations. And then there's a lot of stuff on energy, waves, this kind of thing, because electromagnetic waves and radiation, of course, is very important for our work. So all the rest of it down here is kind of geared up to this with the sort of made up non-physical example running through it. I normally put some reading. It's interesting, if you go on the web and ask for a bibliography on books on electromagnetism, they all date from the 1950s. There doesn't seem to be anything written in the last 50 years that people feel the need to recommend. If you've written a book, sorry, I'm sure it's brilliant. But so, good old Jackson, it says 1998. My version's pre-1998 because I was at university using Jackson well before that. Well, you see, I've tried to put more recent ones on here, but say the Stratton or something is 1953, which is the one most people are mentioning. I didn't put that on. But Jackson, of course, is probably the Bible here. He changes his notation with every reprint. He changes his units with every reprint, so you have to keep alert if you're comparing or picking up an old book when you've been working with a newer one. The others are all sort of fairly standard. Now, Maxwell's equations, as you know, are 4 vector equations. And as my background is mathematics, I mean, they really are mathematical. You have to do some mathematics to play around with them. And when I first of all started giving these lectures, actually to the Stone Accelerator School, and I put up a slide with divs and grads and curls on, I saw people at the back looking rather frantic, and after the lecture they all dashed off to the library to remind themselves what these were. So actually I have produced a 4-page, I think, set of formulae with all these things on basic mathematical stuff. And I suspect nobody has bothered to print that off either, otherwise you should have had that. So I've just put one or two simple things down at the beginning, again, just to remind you, because these are the main ones that I use. So there are three vector operators. If you take a scalar function phi of position and time as well, then you can define the gradient, d pi by dx, d pi by dy, d phi by dz in Cartesians, which is normal to the surface. Phi is a constant. If you have an ordinary three-dimensional vector, you can define two operations, the divergence, d by dx of the first component, d by dy of the second, d by dz of the third, and that's a scalar quantity, it's just a number. And you can also define the curl or the rotation, depending on what you call it, which gives you a vector by mixing up all the components and their derivatives. And these things, they have these names. The names actually are significant. Divergence really does mean things are diverging. So if the divergence is positive, basically you've got a whole lot of rays coming out. If they're just radially straight out, and you can imagine particles traveling on at a uniform rate, the divergence will be a constant. If the rays curve as they go out, then it can be variable. If the divergence is negative, they're all coming in instead of out. And if the divergence is zero, basically they're all just parallel to each other. And of all the many connections between the divergence, the gradient, the curl, and so on, there's really just three, well, four actually, because I've written down here. So the first one is the divergence of the cross product between two vectors, which relates to the curl of the individual ones. There's some fairly obvious ones that the curl of the gradient is zero, all the terms cancel, and the divergence of the curl is also zero. And then there's this one, which is kind of important, but it's a silly one really, because it's meaningless. It's a definition, if you like. Curl is defined. Curl of a vector is a vector, so you can take its curl again. Curl of a vector is well defined. Divergence is defined, gives you a scalar, so you can take its gradient. Gradient of a scalar. But this thing is not defined anywhere, therefore it's defined by this equation. Del squared, the Laplacian of a scalar, is defined, but never of a vector. And so you have to use this. If you want to work out what this del squared is, you actually have to use this combination to work it out. And it's not what you expect it to be in anything other than Cartesians. Okay, but it's nice shorthand notation, and we can compare it with one-dimensional stuff that we're familiar with. So you just have to be careful with that. I've even seen textbooks that have the wrong expression for this later corrected. And then we have two fundamental theorems. Stokes' theorem that relates an integral over a surface to an integral around a boundary. So you have an open surface like this with a boundary all the way around it, and you orient your boundary the normal right-handed corkscrew. So if you go round in that direction, then the normal comes out. Got there. And if you integrate the curl of a function over that surface, it's the same thing as integrating the vector around the boundary. And we need that. And the other one applies to a closed volume rather than an open one. It's the divergence theorem, Gauss's theorem. And this says the integral of the divergence of the vector over that volume is equal to the flux of the vector f out of the surface. So it's f times the normal component of the surface vector as you go out. And we need to use all of those. So what is electromagnetism? Well, basically it's the study of Maxwell's equations. I'll tell you a bit more about Maxwell as we go along. But the equations were produced in about 1860, and what they really did was pull together a whole lot of other results, empirical results, experimental results from people like Gauss and Faraday and Ampere. They just carried out lots of little experiments, made observations. If they doubled the distance, then the effect was divided by 4, so they deduced it was 1 over r squared, this kind of thing. And Maxwell was the one who really pulled everything together and created this cell-contained set of equations. From the point of view of a subject to study, it's rather good, because you can just start with 4 equations and do a whole, just develop it for a whole degree course, if you like, all based on those, without actually having to bring in too much external ideas. So what I'm going to do is to go through these equations individually, remind you what they are, the importance of them, and so on, and then we'll start using them. And the point about these is, I don't know how much of this Jonathan Grattles went into last week. These equations are 1863, so they were 50 years before relativity came along. And these equations were thought to be, well, not wrong, but they would only work in one frame because they didn't satisfy the normal Newtonian transformations that everybody accepted in those days. In fact, what they do is satisfy the relativistic transformations. So Maxwell was 50 years before his time. He produced relativistically, well, not invariant, but the right relativistic equations. They would transform properly under relativistic transformations 50 years before anybody really thought about relativity. And it turned out it was the dynamics that was wrong, and that it's not have to be ordered. So here are the four equations I've written down here on the right-hand side, and they relate all of these quantities, notation. I think this is really there for. So capital E is the electric field, capital D is the electric displacement, and normally these are just proportional to each other. H is the magnetic field and B is the magnetic flux density, and again normally these would be directly proportional to each other. More complicated setups, they will be related by some kind of matrix rather than a single scalar. Rho is the electric charge density, J is the current density, and then we have these constants in here, the permeability of free space, 4 pi 10 to the minus 7, and the permittivity, 3.854 10 to the minus 12, and then they're connected by the speed of light. That's the one you get to remember because it's now exact. It was, instead of measuring it more accurately and adding one more decimal points on, they decided it would end at 8 and that would be it fixed. So if you remember the speed of light and you remember the permeability, because that's 4 pi, that's nice and easy, then you can work out permittivity. And these are related. The product on the mu naught, the epsilon naught, and the c squared is 1, and that's the fundamental quantity that eventually relates light to the electromagnetism properties, and that's how it was that Maxwell's equations really managed to satisfy the relativistic postulates. So over here we have div d is rho, the divergence of the displacement gives you the charge density. Div b is naught, so that corresponds to a 0 density there. The curl of the electric field is related to the rate of change of the magnetic field, and the curl of the magnetic field itself is related back to the rate of change of the displacement with any external applied currents. And that's Maxwell's here. I'll tell you more about him as we go along. So let's take these equations individually and just sort of look at them. So the first one, where it says div d is rho, but if d is just epsilon naught times e, I can put the epsilon naught underneath. And this is just Gauss's flux theorem that I mentioned before. It comes from the divergence theorem. So if we take this equation, div e is rho over epsilon naught, and we integrate it over a volume, closed volume, div e over a volume is E over the surface, so it's the flux of the electric field out of the surface. And from the right-hand side, we get the integral over the volume of the charge density, and therefore you just get a measure of the total charge inside. So Maxwell's first equation is equivalent to Gauss's flux theorem. It just says the flux of the electric field out of a surface gives you a measure of the total charge inside that surface. And here's just a very simple example. A point charge produces a 1 over r squared force, pointing radial outwards. So that's vector r over r cubed to give it a direction. And we integrate that over a surface. So E dot ds becomes, well, its magnitude is 1 over r squared, and it's already radially outwards. So we get 1 over r squared times the surface. But of course, if ds divided by r squared is just the element of solid angle, and if we add up all those elements of solid angle, we just get 4 pi. So this just gives you the 4 pi, cancels it off, and we get the cube over epsilon naught. It measures the charge inside. Okay, and there is Gauss, the prince of mathematicians, who probably predates, I think he was the earliest among the people who were involved in this. Most of his work was done in number theory. His first book was entirely on number theory. The second book had a lot of number theory in, but then he turned to astronomy mainly, a lot of predictions of unknown planets or stars that were discovered as to where they moved. He made his name because somebody discovered, I can't remember the name of it, some planet or comet, and they managed to measure it. I think it was probably only 10 degrees of an arc to take some measurements, and then it disappeared behind the sun. And all the scientists at the time frantically got to work to try and work out where it would appear, where it came out. And most of them agreed, gave the same answer. Gauss came back, gave a completely different answer. And of course, when the planet appeared, it was exactly where Gauss had said it would be. Gauss wouldn't say how he'd done it, but apparently he'd invented the method of least squared fits, and he'd used that. It wasn't known at the time. This was about 1750. But of course, his flux theorem is very well known. Most of his work was eventually done in industry and things like that. The only other thing I know about him was he got very cantankerous in his old age. People would bring him papers and say, look, I've come up with this wonderful idea. And he looked at it and he says, yeah, that's right, but I did it 15 years ago. Let's discard it. Maxwell's second equation, well, if you like, it's Gauss's flux theorem for magnetism. So instead of div D is rho, it's div B is naught. So I said no pole charge density, which corresponds to the fact that there are no magnetic monopoles. If you take a bar magnet, which has got a north pole and a south pole, cut it down the middle, where you cut it, you generate another north and south pole. So they're always in pairs and so on. And the corresponding thing here from div B is naught, is the flux of B out of any surface is 0. So here there's a magnet with the field lines on. You take any sort of circuit like that, then it's 0 because if you look at all the field lines, well, the total inside plus minus comes to 0. If you take a circuit out here, it's 0 because you've got field lines coming in here and then coming out on the opposite sides, so they will cancel out. At least nobody's ever found a single magnetic monopole, although they often look for them. Okay, so the third equation, now we're bringing in type. The others are just static. So now curly is minus the rate of change of B. And this is just Faraday's law, Faraday's empirical law of induction. So if you take this equation, because it's a curl equation, you're going to integrate it around an open surface with a boundary. So if you integrate curl of E around the open surface, it's the same as d by dt around the surface. Curl of E around the surface becomes E around the boundary, which is the electromotive force measured around that circuit. And on this side, take the time derivative out because it's independent of the space derivatives. And then you've got integral of B dot ds, which is the flux of B out of that surface. So what you're saying is the electromotive force around the circuit is the negative of the rate of change of the flux through that surface. And this is the principle behind the electric motor. If you can make your flux vary that flux in time, then you're going to generate an electric field that can be used to drive something. And Faraday, of all people, well, there's some silly little animation where it's a bar magnet going inside a coil, so it varies the magnetic flux through it, and you get a reading on your galvanometer or something. And that is Michael Faraday. He's quite an interesting character. He had no education at all. His parents were very poor, so he didn't have much in the way of schooling. Basically, he just taught himself to read and write. And when he was 14, he was apprenticed to a bookbinder. And he started reading all the books that came in, as you would naturally if you're binding books. You turn the pages and look at them. And he found the books on science fascinating. When he was, I think, 17, he went along to the Royal Society to some lectures given by Sir Humphrey Davy, who was the president. And I think there were some other lectures as well. And Faraday took copious notes and went back and wrote them all up into a 300-page volume, which he bound himself. And he took them along and presented them to Davy. And Davy was so impressed with this, he offered Faraday a job in his laboratory. Faraday eventually went on to become the director of the lab. And he was not president of the Royal Society. He refused that, but he was asked 2 or 3 times to take over. Like so many of the scientists in those days, they dabbled a lot in chemistry. So I think he discovered benzene. He was the first person to liquefy fluorine and so on. Did a lot of work on the periodic table. But the thing he's, of course, most famous for is Faraday's law, because it's the basics of what you see around you in the world today. He was also, I'm told, an absolutely brilliant lecturer. So I'm sorry you haven't got Faraday, you've got me. And was also said to be one of the greatest experimental physicists that's ever lived. So he wasn't a mathematician. In fact, his maths was appalling. He hardly knew any trigonometry or any geometry. But I think it was it Maxwell? Yeah, I think Maxwell it was who looked into his work and talked to him and said he could have been an absolutely brilliant mathematician if he'd had the training. And then the fourth equation. So curl of B, if you change it from H to B, will then be mu naught J, and then this was d capital D by dt, and if D is epsilon E, then dE by dt, and the epsilon naught mu naught has become the 1 over c squared, the speed of light. And this is Ampere's law. Well, Ampere's law is not quite this. Again, Ampere didn't put it in mathematical form, but basically Ampere's law is just the beginning. Curl B is mu naught J. So the current gives you the magnetic field. You have a current flowing down a wire, then there's a magnetic field around it. And again, because it's a curl equation, we can integrate it around an open surface. The integral of curl B becomes B dot dl around the boundary. And over here, the integral of J dot ds, as J is the current density, gives you the current I that flows through your surface. So integrating B around your boundary tells you how much current's actually flowing through it. And one example of this is the, well, again, Biot-Savart law. You take any old current wire, then Biot and Savart, again, it was experimental. They said the force, the magnetic field generated goes like 1 over r squared, the distance, and there is a constant, it's linear in the current, and so on. So they came up with a formula that was basically this, apart from some constants, of course, depending on your units. So in modern mathematical form, this is the Biot-Savart law. It's 1 over r squared, vector r over r cubed, and right angles to the element of length. So if you just take this as a straight line rather than a curve, it just becomes mu naught I over 2 pi r, a very simple formula. And this is Ampere, and there's Biot. I didn't put Savart on. Ampere is also a very interesting character. He was the complete opposite to Faraday. He was a rich guy. His father was something high up in, well, in the aristocracy, if you like, in Paris, around the time of the French Revolution. And in those days, sending kids to school was frowned upon amongst the affluent. You taught your kids yourself. So he was left to his own devices with his father coaching him. But he had access to all the main books and so on. So, and he worked hard and he studied all kinds of things. At the age of 12, he declared he knew everything there was to know about mathematics. And so he wrote a paper and he sent it off to the French Royal Society. No, it would be royal, whatever it is, the main French society. And I think it must have been Cauchy who was the president. Anyway, it was rejected and sent back to him. And that which shook him up. What he'd effectively done at the age of 12, 13, was discover calculus. He didn't know it, he hadn't come across it. And his paper was all on twisted curves and so on. So he basically had to invent calculus, a way to treat something that's not linear. But that shook him up, so he realized there was a lot he didn't know, and he knuckled down and got on with it. So he was the one, he's responsible for the theory of games. He invented the theory of games. He invented the calculus of variations, which again is fundamental in many branches of physics. He did an awful lot of work. As I said, these mathematicians, physicists dabble in everything. So he did a lot of work in chemistry as well. A lot of work on the periodic table. And of course, all of this in electromagnetism. A lot of it in electromagnetism was, well, before, again, other people. So, for example, he discovered the law of electromagnetic induction, which is now attributed to Faraday. Faraday did it independently, but Ampere just kept quiet and let Faraday take the plaudits for it. I think about 10 years before he'd discovered it. A lot of the stuff he didn't write up until other people wrote it up, and then he suddenly had to sit down. So I think Ørsted published something on electromagnetism, and Ampere realised that he'd been working on very similar lines, and so virtually sat down and in the space of a month produced a vast tome that included all of this stuff here. Bio was sort of an army man, worked in the army and didn't much like it, eventually got out and took to mathematics. He was a professor of mathematics at a couple of the main French universities. And he's most famous really for this equation here. He did do some work in geometry, and I think he won what's called the Rutherford Medal of the British Society for his work in geometry. But I was sorry for Ampere, because his was the equation that was wrong. If you go back, see that's Ampere's equation there, and yet Maxwell's equation's got this on it. And you can see that it's wrong, because according to Faraday, if you vary the magnetic field, change the flux, you will generate an electric field. And so Maxwell says, well, why doesn't it work the other way around? Why, if we change the electric field, can we not generate a magnetic field? There was nothing in those equations to suggest this. And you can see just by, there's a very simple example here, you can see what's missing and put it right. So here is just a parallel plate condenser with a current I coming in and coming on. And you take two surfaces and you apply this flux rule. So just take a flat disk here, surface 1, where the current I is flowing through it. If we apply the rule we had before and you do the line integral round it, integrate round with B, then you'll get a measure of the current. The B will be the mu naught, just come out to be mu naught. But if we apply it to this curved surface that goes around here through the gap between the plates, your flux integral will actually be 0 because there's no current flowing through it. And yet, according to all the mathematics, you get exactly the same result no matter what surface you choose. So something's missing in this. What's missing is the fact that if you take a parallel plate condenser, of course you put charge Q on the plates, the area is A, then there's an electric field between them, Q over A, and then the current, which is the rate of change of Q from this, just becomes the rate of change of E. There's a dE by dt term coming in. So the electric field is just given by the epsilon naught, the area, and dE by dt. And this tells you that, the current is given by that. So this tells you that you should really have an extra term, a current density term in the current I divided by A, which is epsilon naught dE by dt. And if you add that term in, so you have not just the ordinary current density here, but you add in this displacement current density, JD, in the gap, then your equations will work. Because if you take the equation curl B and you integrate it over a flat surface, you'll get the current contribution from the J and nothing from the JD. If you take the curved surface, you'll get nothing from the J, but the JD term will give you the term you want. And then it will all be absolutely consistent. And then this is Maxwell's equation, the extra term added in, the dE by dt. You then get the result that if you vary the electric field dE by dt, you generate the magnetic field back. And then it's all consistent. One of the nice things about these equations are that you don't actually have to add anything else in. Normally you need some extra postulates, conservation laws, one of them. So if you're doing fluid dynamics, you have equations for the motion of the fluid, but you always have to apply externally the rule that says the fluid can't be created or destroyed. It would change its shape and its density, but you've still got the same number of fluid particles, if you like. And you'd expect the same thing with charge density, but it's actually already inside Maxwell's equations, it tells you. So I'll just show you here it's done two ways. So we can do it as applying some physics. The flux of the current out of a surface gives you the rate of decrease of the charge inside. So negative because it's decreased, rate of change off, and that's the charge inside, the integral of the density of the volume. So take the d by dt inside, it becomes d by dt here. The j dot ds, j over the surface, converts to div of j over the volume. So now you've got two volume integrals, and the volume is absolutely arbitrary. You can shrink it down to a point. So you can cancel off these integral signs, and you've got div j plus d rho by dt is naught, which is standard conservation law that you see in so many different branches of physics. But if you take Maxwell's equations, you can see you get the same thing. So from Maxwell's equations, curl B is the J and the d E by dt. Take the divergence, or the divergence of the curl is 0. Here we've got div J, and on this one we're going to get div E. And div E from the first Maxwell equation is rho over epsilon naught. And when you put that in, cancel the epsilons off, lo and behold, you're back to the same equation. So it's implicit. Charge conservation is implicit inside Maxwell's equations. We don't actually have to add it anymore. So here's a sort of summary. Those are the equations. I've written them down as the source-free terms, the ones that don't involve charge density and current density, and then the equations that do have the sources in. And there is the equivalent version on the other side, which sort of engineers are more familiar with, which talk about the flux. The flux of E is proportional to the charge inside. Flux of magnetic field is 0. The electromagnetic force is the negative of the rate of change of flux. And then the integral of B around a circuit, usually these current density terms. So the thing about these is that they apply at points. So any individual point they hold. These are integrals, and therefore you add it up, you've summed. So those are global expressions, but they're exactly equivalent to each other. You can use whichever you like. And there is Maxwell himself. I call him the man who changed everything. He was the guy who came along and took all these empirical results, pulled them together and started thinking about it. But he was the one who made the astounding proposition that you didn't necessarily just need to think of electricity as flowing through currents and energy going, through conductors and material, that you could think of it pervading the whole of space. It could be magnetic fields throughout space, electric fields throughout space, and so on. And that they were all tied together. As I said before, if you vary the magnetic field, you generate an electric field. If you vary the electric field, you generate the magnetic field. Every time a little magnet shakes, a pulse goes out through the ether and so on, and there are electric fields and magnetic fields everywhere, and the same thing. And he was the one who pulled all of this together and created this whole theory. And without him, well, unless somebody else came along, the world wouldn't be as it is today, because we rely on electricity, magnetism, and so on all around us in everything we see. So he united electricity, magnetism, and at the same time realized that this is tied in with light. I'm going to do electromagnetic waves very shortly. But throw that away, and he would still have been an incredible, one of the greatest scientists who ever lived. He did so many other things. He was a funny little boy at school. His parents lived just south of Edinburgh, and they sent him to school in Edinburgh. But they dressed him in very old-fashioned clothes, even for the time, and he got his leg pulled about it, but he didn't care. He was more interested in the world around him. You know, he was always nosing down drains to see where the water went when it ran through them and so on. Always trying to find out how things worked, what was going on, what was behind them. With his funny little, what did he call it? What's the go of it? I can't do a Scottish accent. Instead of saying, how does it work, he would say, what's the go of it? What's the go of it? And if somebody gave him a hand-waving explanation, yeah, but what's the real go of it? He actually wanted to know everything. So he found out the ways in which we perceive colour, and used it to take the first ever colour photograph. He is the founder of information theory. The origins of that are attributed to him. He wrote the first papers on control theory, and these are used today. His ideas are used in modern control theory today. He's the father of statistical physics. He's the first person to suggest that statistical techniques could be used in subjects like thermodynamics and so on. So each one of these are really big theories that he's responsible for. He was the first person to use sensibly what are known as thought experiments, which Einstein used a lot later on. Not real experiments, but just thinking about things. So he came up with the idea of Maxwell's demon, which was this little creature that could help heat travel from cold regions to hot regions. And it took 30 years before anybody could see any kind of flaw in the argument. So it made you really think about. he used polarized light to reveal the strain patterns in structures. And finally, he came up with the idea of using a centrifuge to separate gases. So many different things that he did in his lifetime. You can see from that, he was only 48 when he died as well. Maxwell's equations were produced when he was 30, so he really only had 18 years of his life in which he did this. Right, a simple example, which does lead into accelerators in a way. Suppose, well, here I've got a magnetic field, an oscillating magnetic field just going up and down as a sine wave. And it's confined to this region, which has a radius r0. Okay. So the magnetic field is just B0, a constant sine omega t within that shaded region, and it's 0 outside. And here is, well, Faraday's law. And what we want to do is to use it to find out what electric field this will actually generate. So we've clearly got to look at the region inside where the field is and outside where there's no magnetic field. So first of all, we need a circuit. So let's just take a little loop which has a radius that's smaller than the R0, the maximum radius, and work it out. So you can do the calculations here. The electric field is, so the magnetic field is going up and down, the electric field is going to go round in a circle. So if we work out E into E dot dl, E is just in the angular direction, E theta. It's a constant all the way around the boundary, so we multiply by the length, 2 pi r. Over here, minus the rate of change of, and then it's B over the surface area of the little loop, which is pi r squared, radius r, the B0 sine omega t. So if we differentiate that, we just get cos omega t coming out. And so from that, you deduce an electric field inside this region, which is linear, is proportional to r, so it just grows linearly as we go out to the boundary. If we take another circuit, but this time outside, rather larger, we can do exactly the same thing. The left-hand side is still the same, but the right-hand side, the flux of B. Now, well, there's no flux through this bit, so the flux is just the flux over the shaded part. So instead of pi r squared, it's pi r0 squared. So exactly the same thing, but with an r0, and then when we divide, instead of getting linearly proportional to r, we find it's proportional to 1 over r. So the field inside increases linearly with r, and outside it just falls off by 1 over r. You can go back and do it from the equations as well. I've done it from the integral form. Just do it from curly is minus dB by dt and integrate it up. You're going to get constants coming in, and you have to match them across the boundary from the outside to the inside, with some other fairly obvious physical assumptions, such as it will go to 0 if you go an infinite distance away. And then if you wanted to, you could go back to Maxwell's equations and find out what current would be needed to sustain this thing in the first place. And this is basically the idea behind what's called Betatron. You vary a magnetic field up and down, and it generates an electric field around. And if you can vary your magnetic field in the right way, you can create just the electric field you want to hold your particles and accelerate them as you go around. It's actually rather difficult to do. And what you find is that if you want to maintain a constant radius for your orbit, there's a result down here that puts a rather difficult constraint on you. So here we have the equation here. The integral E dot dl round our circuit is 2 pi r times E theta, and then this is the rate of change in flux. So suppose we have a constant radius, then the equations of motion say the centrifugal force mv squared over r, velocities, got to match the force that comes from the magnetic field, a v cross b force, ev v. And that tells you that the magnetic field is just from this, the momentum mv divided by the charge and divided by the r. So if I then want to look at the dB by dt, that's going to come in here. dB by dt is just given by the rate of change of p, and the rate of change of momentum is given by the force from Newton's law, and the force is the electric field. Okay, so there's an so that's going to tell me that E over R is given by, and then the dB by dt going back up here is going to be, well, it's the flux, but I've got to divide it by the pi r squared. And so if this is a time derivative and that one's a time derivative, I can integrate that to get rid of the b's. It tells me the b comes out to be a half 1 over pi r squared times that flux term itself. And so that's the flux through the surface. I divide it by the area, so that's the average flux through the surface, and it's got a half. It tells me I've got to set it up so the field actually on that orbit is 1/2 of the average field over the inside. So it's a rather sort of difficult constraint to do. And you're limited as to how much energy you can get into the particle, into your particle as a result of that. So the Betatron was it was cursed and so on around that area. It was invented, but it was taken over by the idea for a synchrotron more or less around the time. So you don't come across many examples of the Betatron nowadays, other than little things like this. This is just a very small sort of X-ray generator. So there's a little electron gun sending a beam in, the magnetic field up the middle, and a toroid with some magnets in there. So that's a little commercial one that's using this kind of principle. Okay, the other aspect of Maxwell's equation is just the 4 equations themselves. You can actually deduce what the boundary conditions should be from them. Again, we don't have to impose external ideas for the boundary conditions. So if you take, for example, div b equals 0 and take a surface at some kind of interface, you can work out how b changes across that interface. So what I've got is just a little cylinder here, just this little tiny pillbox, if you like, across the surface, going from the side I've marked as minus to the side as plus. And we integrate div b over it. Well, we know div b is 0 from Maxwell's equation. So if I integrate b over the volume of this, it's the same as b integrated over the surface, which is 0. But what I'm going to do is shrink that down. So the curved surface around the outside is going to go to 0. I can forget about that. So basically my surface is just made up of the flat surface at the top and the flat surface at the bottom. Right, and the normal is pointing out, so at the top it goes up, the bottom it goes down, and if I turn the bottom one round to maintain the direction, of course I bring the minus sign. So what I finish up with on this b dot ds is the normal component of b on the plus side, but minus the component going upwards of b on the minus side, times the surface area down to s is 0. Okay, and then from this, what I'm deducing is the normal component of b doesn't change as I cross that boundary. Okay, so it's the same on the minus side as it is on the plus side. If I do the same thing for div d equals rho, applied to exactly the same thing, it's going to go through as before, but instead of 0 coming in there, I'm going to get the charge density. And I will work out how much charge there is in that little cylinder, which is just obtained from the charge that's sitting on the surface. So, corresponding to this, I get the same thing with d, but instead of the 0, I get the charge density on the surface, sigma, times that surface area. So if you cancel off the surface area, it tells you you have a jump in the d field in the electric displacement as you go from one side to the other, which is given by the surface charge density. Okay, so that's 2 of Maxwell's equations that give you constraints on the normal component going from one side to another. If you take the other 2 Maxwell's equations, which are the curl ones, then you can deduce results about the tangential components. So here you just take a surface and you put a little loop going round. And we integrate round the loop. So as before, curl of E is minus dv by dt. The curl of E will integrate to the electromotive force, E dot dl, around that circuit. And the dB by dt is going to go to the rate of change of flux through that circuit. Now I'm going to shrink that circuit down either side. In fact, the surface area will go to 0, and therefore there will be no flux coming through. So this will actually go to 0 when I shrink it down. But this thing, E dot dl, E round the boundary, well, I've got a tangentially that way, and here I'm going in that direction, so I get a minus sign turning it round to make it the same direction. This is going to go to 0, I can forget about it. So what I'm deducing is that the parallel component, the tangential component of E on the 2 sides, the difference between them is 0. So tangential E is conserved. Coming from this equation, if you take the corresponding one for H, where we now have a source term, a J coming in, I'm going to go through exactly the same mathematics, the change in the tangential component of H there is that on this side I get a contribution from that J, and that will give me the surface current density, which I call capital K. So I have a current density K times the length. And this tells me that the jump in the tangential component of H is given by the current that's on the surface. So all the boundary conditions come in from Maxwell's equations. Okay. Right. Normally in electromagnetism you add in the Lorentz force law. Actually, you don't need to as well. If I could do this one level up, so totally in terms of relativistic notation and so on, then the Lorentz force law actually just falls out. It's there naturally as well in the relativistic formulation of Maxwell's equations. Because I've done it rather classically just by writing down the curl equations and so on, I can't show you how it just deduces, so I've actually had to write it down. So the Lorentz force law says the force produced by electric fields is proportional, directly proportional to the electric field itself, QE, but in terms of the magnetic field, it's V cross B, where V is the velocity of the particle. If instead of a single charge you have a charge density, then you will have a force density. The charge will become a charge density rho, and the charge times its velocity is the current, which will become the current density J, so you get J cross B from distribution. And then these were from the relativity lecture, the four vector form. The force four vector is the rate of change of the four momentum vector with respect to proper time. And if you write down the components of these and relate to the four momentum vector, then you can look at individual components. So, for example, the three vector components is F, the gammas will cancel. F is the rate of change of the three momentum, and the three momentum is the rest mass m naught gamma v. So rate of change of m naught gamma v is the Lorentz force up here, which is the QE plus V cross B. And the other one says the rate of change, sorry, this is E without a vector line on the top, is the energy of the particle. The rate of change of the energy is proportional to V dot F, the rate at which the force does work, as you'd expect from classical expression. So V dot F gives you the rate of change of the energy, relativistic energy, or gamma. So those are the two equations. Well, that's the first equation I've just written down. I've just got two slides here. First of all, a constant magnetic field, and then a constant electric field again, just to remind you what happens in these. So if you take just an electric field, just a magnetic field, so there's no E, this is just QV cross B. So the rate of change of m naught gamma V is QV cross B. So you can, and then the energy one, rate of change of the energy is V dot F, but that's V dot V cross B, so it is 0. So the energy doesn't change, the gamma is a constant. And if gamma is a constant, the magnitude of the velocity is going to be a constant, the total velocity is a constant. That means you get no acceleration if you've got a magnetic field. Again, you should know that. So we actually need the electric field for the acceleration. The magnetic field is used for the confinement, focusing. The other thing we can do is to take this equation, and because that is perpendicular to B, we could dot it with B. If I dot it with B, I've got B dot this will be B dot that, which is 0. If I take the B inside, I've got B dot V. So the rate of change of the component of V along the magnetic field is 0. Component of V along the magnetic field then is a constant. So the total velocity is a constant, sorry, the total speed is a constant, the component along the magnetic field is a constant, and therefore the magnitude of the component transverse to the magnetic field must also be constant. So the parallel component to the field is a constant, and the transverse component. Change of direction, of course, but the magnitude is a constant. And from this you just deduce that you actually just get motion in the circle. So if these are constant, I can write down the equation of motion here. The gamma is a constant, so it comes straight out and go over this side. The acceleration term dv by dt is the centrifugal acceleration, which is given by the perpendicular component squared divided by rho. And over here, just working out that, it's just v times v. So if you rearrange this, you can get the radius that's coming out of this. The constant radius for the circular motion is related to the momentum and the magnetic field. And there's an angular frequency given by the velocity over rho, QB over m, which is the cyclotron frequency for this. And so what you deduce is you've got circular motion about the magnetic field. The component along the magnetic field is unchanged, so you're going to get a spiral. So in general, just a magnetic field with spiraling of your particle. And that equation, of course, is quite important because if you rearrange it, that's right, multiply up by the B, you get this expression for what's known as the magnetic rigidity, which Mike Poole probably told you about in his first lecture. B times rho is given by the momentum. So if it tells you, if you have a certain magnetic field, what the bending radius is going to be at a certain energy, or the other way round, if you're confined, so you've got to bend within a certain radius, then it will tell you how strong your magnetic field has to be to make it work. Now, I'm not going to do the electric field because although the electric field normally seems simpler, it's not. So if we've only got an electric field, there's no V cross B, so the rate of change of the momentum is Q times E, and then you might say, well, that's trivial, I can integrate that straight up. Well, you can, but then it gets a bit messy after that. So I can integrate it straight up once, the time just goes straight up onto there, and so you just use this formula for gamma V, but the problem is that the gamma's got the velocities inside it. So sorting this out and getting the velocity, you finish up with a square root coming in, and then you've got to integrate up your square root. And you finish up with a formula for the position if you're travelling in the x direction, which has got this square root in. So if you had a constant acceleration, you would normally think of the curve as being a parabola, just like gravity or something like that. It's not actually a parabola here, it's this square root of 1 plus the t squared minus 1, and it only goes down to the parabola in the limit of low fields. So this is the effect of relativity, or bend away from the parabola at higher fields. Okay, so as I said before, you need this electric field to give you a uniform acceleration. And I haven't put the two together. The E and the B together, constant, will each produce this kind of motion, but they will interact with each other. And you probably know you get a drift called the E cross B drift at right angles to the bottom. Oh, that's some silly little thing. That's the parabola. How are we going? Okay, I'll just do this slide, or perhaps this slide, the next slide, and then we'll have a 10-minute break or something, or 15-minute break, and then I'll carry on after that. So I mentioned at the beginning that Maxwell was way before his time because his equations already satisfied the transformations of relativity, although they were thought wrong because they didn't fit into the structure in those days. So how do these fields E and B transform? We can do a bit of hand waving here. Right, so what I've got here is, it's a matter of just looking at particles from one frame to another. If a particle is at rest in front of you, then somebody in a moving frame will actually see it relative to them. They'll see this particle is moving, so it will then become a current, and vice versa. So let's take an observer O who's sitting in the frame F, and he sees a particle moving with a velocity v in E and B fields. So there's a Lorentz force QE plus V cross B. That's what we see. Now suppose you jump onto the frame of the particle. So here it is, it's there in front of you, you're holding it, it's not moving. So if you move to a frame F prime where the particle is at rest, then the V cross B doesn't come in, there's no V. So all you're seeing is a force which is just Q times E. We don't know if it's the same E, we don't even know if it's the same Q, we don't even know if the force is the same, which is why I put primes on all of them. But there's no V cross B term in that because B is 0. So we make an assumption. Let's assume that we see the same force. And let's assume that the charge doesn't change. Then you've got a connection between the E. It tells you the electric field in the rest frame is equal to E plus V cross B back in the lab frame. Okay, so that's one way. It's not right, but okay, it's not far wrong. It's a reasonable idea. And let's do it the other way around. think of point charges at rest and then moving, creating currents and so on. So let's take a point charge at rest here in the lab frame. It produces 1 over r squared force law and doesn't produce a magnetic field. So F is r over r cubed, B is 0. Now we go to a different frame that's moving with a velocity v with respect to it. Then you'll see a current, and the current will be given by that Biot-Savart law that we had before. So the current is q times the velocity, qv cross r over r cubed with the mu naught and 4 pi. And if you look at this, you see the vector r over r cubed and the q over 4 pi and so on is back in the E field. So you've got a magnetic field that's related back to the E field in the other frame. So this suggests that if you started with a B field and then you do the transformation, then the B field you get at the end picks up this extra V cross E term. Okay, so there you have 2 possible transformation tools. And they're near enough right, just from hand waving. They're not right. So it's only a rough idea. And so what you've got to do to get them right is, sorry, it's covered it up, but it said E is E plus V cross B. It only works at right angles to the transformation. In the direction of the motion is left the same. That's the opposite to a standard space-time transformation relativity, where it's the component in the direction of the motion that changes, the component at right angles that doesn't change, the opposite way around. And you might have guessed what was wrong in the formula is the gamma's missing. You always have to have a gamma on the outside, it seems. This other one I had down here, you see, it's almost right as well, except for the gamma. And again, it's the perpendicular component that it applies to, and not the parallel component. Okay, I think I'll stop there.